Okay, welcome to chapter 17, where we're going to talk about climate change. And in this chapter, we're going to look at several things kind of related to the topic of climate change. First, we're going to talk about how Earth is a greenhouse planet, exactly what that means. Then we'll give some evidence for climate change. Then we'll talk about our increase in knowledge of about global warming and climate change. And then we'll talk about impacts and some of the primary greenhouse gases that are affecting the change of climate. We'll talk about our current state and consequences of climate change, and then we'll look at how we could potentially address climate change issues. Now, the first thing we're going to start off with is, looking at the fact that the Earth is a greenhouse planet. And what we mean by this is that Earth is pretty unique in that it has a temperature that allows water to exist in liquid form. All of the other planets in the solar system are either too hot or too cold for water to for water to exist in liquid form. And water in liquid form is what allows our biological processes to happen. It's what allows life, kind of big properties to function. Our bodies are over 50% water. All of the early forms of life develop in the ocean. So not only is it important for the functions of our cells, but life also developed in aquatic environments, as far as evolutionary evidence suggests. Um, and so the presence of liquid water is important for life, as far as we understand life. So basically, life as we know it. And so, if the Earth was not a greenhouse gas and did not allow for water to exist as a liquid, then life would either have to be very different from what we see now, or it wouldn't have been able to exist at all. Now, the Earth's temperature is determined by a couple of different factors. First is the distance from the sun. So if you're farther from the sun, you're going to be colder. If you're closer to the sun, your overall temperature is going to be hotter. But now our planet is a little different than most planets in that it also has this atmosphere that is made up of specific gas concentrations that cause the greenhouse effect to happen, and we'll talk about that in a little bit. The presence of carbon dioxide in the atmosphere is another big factor. So as the Earth orbits around the sun, you'll get small changes in distance. And so the energy um, of the sun changes around a decade, 11 years or so. But the differences are so small you can't really notice that change. And so this bullet actually probably should be right here. Um, And so just kind of going off of the presence of carbon dioxide, this kind of follows or leads us into the discussion of the greenhouse effect. So like I mentioned, there are several gases in the atmosphere. What's interesting about these gases is that they're transparent to solar radiation. So they allow for ultraviolet radiation, visible light energy, to go through the atmosphere, but the atmosphere absorbs this infrared radiation. The gases that make it through, so the ultraviolet and the visible light, they penetrate the atmosphere and then they're absorbed by the Earth's surface. Now, as the Earth's surface absorbs that light, right, so let's say this is the surface of the Earth, you have that radiation coming in, and so that increases the temp of the surface. but then that surface will re-radiate that energy back up. Okay, and now when it re-radiates that heat back up, it's then absorbed by the greenhouse gases in the atmosphere. So you're basically getting the effect of a greenhouse. And so the atmosphere, let's say this is the atmosphere, is basically preventing a lot of that heat, right, from making it back out into space. And so it's essentially the same thing that a greenhouse does. Right, so let's say you have a greenhouse, it's clear, has those kind of glass panels. The light comes in, and then as it goes to re-radiate back out, it can't penetrate back out. And so inside the greenhouse, right, is much warmer than the outside, right? Let's say if, it'd be like a 10-degree difference or so. And so that's essentially what our atmosphere does. Our atmosphere basically does the same thing that a greenhouse does in terms of temperature. And so that effect is known as the greenhouse effect. So that process, that phenomenon, is what we call the greenhouse effect. Carbon dioxide is a greenhouse gas. It is one of those gases that lets solar radiation through and then keeps that solar radiation from going back out into space. And now, I should actually say it doesn't prevent all of it. There's some energy waves that do make it back out into space, but it keeps a lot of that energy from going out into space and leaving our atmosphere. The amount of carbon dioxide in the atmosphere is actually small relative to other concentrations. Remember, we talked about that in our air pollution chapter. But its effect in terms of the greenhouse gas effect is actually pretty significant. So for example, NASA did a study. If there were no carbon dioxide in the atmosphere, the Earth's temperature would be about minus 18 degrees Celsius, which is 0 degrees Fahrenheit. So liquid or water would be ice, right? So that's below freezing. And our current temperature is actually 15 degrees Celsius or 60 degrees Fahrenheit. That's a big difference, right? In just a relatively small amount of carbon dioxide. So carbon dioxide is really big, plays a really big role in the Earth's temperature in terms of a greenhouse gas. And so the greenhouse gas effect that has that carbon dioxide in the atmosphere, right, is what makes water liquid or keeps the Earth's temperature at a range that allows water to be liquid at the surface of the Earth, and is what makes Earth suitable for life that we know now. This image here is showing the greenhouse effect. There we go. You got all your solar radiation coming in. So you got that radiation that passes through. You got some reflected by the atmosphere, some reflected by the Earth. All of this is being absorbed by the Earth. That solar radiation that's absorbed is the infrared radiation is emitted from the Earth's surface. Some of that will pass through the atmosphere. Some of it is absorbed and then re-emitted, kind of in all directions. And so you have a little bit going out into space, and then you have some coming basically back down to the Earth. And so that overall effect is the warm Earth in the lower portions of the atmosphere. Okay. And so that's kind of where our current temperature lies on Earth, or the reason why the Earth's temperature is what it is basically what we see as an average. Now, what I want to talk about next is the terms that you may hear related to climate change. And so you hear these phrases probably often related to climate change, and that's the term climate change itself, but then also the term global warming. Um, People will use these terms interchangeably when they really shouldn't be used interchangeably. They're actually very different aspects, but they're all related to kind of the same problem. And so just to kind of clarify what we mean when we use these terms, okay? So global warming is the average temperature change in the Earth's atmosphere. So overall, after all of the changes, all of the regional and local changes are accounted for, the Earth's temperature is increasing and is predicted to increase and overall warm. Okay, so we say that global warming is happening. So the Earth is warming on average due to climate change, right? Climate change is the changes that are occurring, okay, um, and those overall changes are leading, right, are culminating, there we go, are culminating, right, in that overall warmer temperature, okay? So for example, in different parts of the world, so let's say like in the southwestern United States, it's probably going to get drier and hotter, but maybe in the Northeast, it's going to get colder and wetter, right? And so people will say, oh, well, I thought, if climate change or if global warming is happening, how is it that, the Northeast is getting colder and is having more rain? That doesn't make sense. Um, well, actually, right, if you think about it, the overall changes, the local changes are variable. And so some places will warm, some places will cool, some places will be drier, some places will be wetter, some places may not change that much, but I highly doubt it. And overall, you get a global warming effect, right? So after you account for all of those changes, you end up with a higher average global temperature, right? And so that's what we mean when we refer to these two terms, okay? And so what I say is I always use the term climate change because that's the term that really kind of gets at what's actually happening in terms of explaining it to people. So I like to use climate change more often and try to stay away from global warming. Although I'm not saying global warming is incorrect, but it could be incorrect depending on how you use it. Whereas climate change, you're talking about changes, whether it's warming, cooling, drying, getting wet, etc. And understanding that that's variable across the globe in relation to the overall global warming that we're seeing. Okay. And what's really interesting is that throughout Earth's history, we have geological evidence, we have, you know, climate evidence that has allowed us to understand and, surmise that the Earth has undergone several, many different episodes of climate change over time. And that climate change has been significant. Um, Millions of years ago, the climate change has changed much more substantially than changes that we're predicting over the next 100 years. The big issue, though, is the rate of climate change, right? So, if we say that climate has changed, 8 degrees Celsius, and this may not be correct, I'm just making numbers up here. So let's say if it changed from 8 degrees Celsius from 60, I don't know why I put a degree there, but 60 million years ago to 40 million years ago. I did it again. 40 million years ago, right? So if there was an 8 degrees Celsius change from 60 million years ago to 40 million years ago, that 8-degree change happened in 20 million years, right? Now, we're saying that our highest estimates are going to be somewhere around 6 degrees Celsius in terms of overall global temperature change. That's if we don't do anything to affect our carbon emissions, to lower them or reduce them. And so we're looking at an average of that change somewhere between, get my numbers right, 2050 and 2100, right? Depending on the models you look at. That change is going to happen somewhere between this time frame. This is a much faster rate of change, right? So even though this one is a higher overall climate change, it happened over 20 million years, whereas this one is a lower climate change, but it's happening, it's 2021, so this is 29 years. Is it 29 years? Yeah, 29 years. And upwards to 79 years. And so that is a very rapid change, and that's kind of what some of the big concern is that change too fast for ecosystems and organisms to cope with? And a lot of studies have suggested that that is the case. And that's kind of our big concern, is that rate of change is so rapid. We have evidence that North America was covered by large glaciers at some point in time. If any of you have ever seen, the movies Ice Age and oh gosh, what is that? The Day After Tomorrow. Those are all like really big, climate related movies. And are part of these cooling events. The Ice Age is related to the big ice sheets, but The Day After Tomorrow is interesting because it's a little fictional. It's a little, it's very fictional as of right now, but it has those rapid cooling changes that could have potentially happened in the past. And I say fictional because it's, it had been, what is the term, Hollywoodized, or whatever you would say. Anyways, so this is an image of some continental glaciers. So you had the larger Laurentide ice sheet, which actually came pretty far down. And so what is it? You've got San Francisco Bay. So California is about somewhere like this, maybe. And I mean, this is North Carolina right here. Maybe I pulled it a little farther out. Tennessee, I like South Carolina, I like Georgia. I'm drawing it too far out, but then you have like Alabama, Mississippi, and so this is like Arkansas, Oklahoma, out in here. That's really close to the ice sheet. So it was pretty far down. So New York and Ohio and Indiana, they were all covered by ice at one point in time. And this ice sheet is, or was, very, very thick. We're talking about miles thick. It wasn't no thin ice sheet. You have the Cordilleran ice sheet, then you have ice sheets up here, and then you even had glaciers in the Sierras. So Yosemite Valley was carved by glaciers. And so even though they weren't large ice sheets, you did have glaciers in pockets all around the United States. And so this is kind of showing even relatively recent changes in temperature. So you can see from 1880 till about the early 1900s, so like 1936, it was relatively cooler periods. We had a little warming blip, then we had some cooler blips with intermittent warming, so some warming cooling episodes. But then around 1980, we start that hockey stick trend that we'll look at in a little bit, where we see that rapid increase in temperature change. And now this is deviations from the long-term average, right? But the big idea here is that we're now in this very warm deviation, right? So we have that overall warming effect. And so there was really significant things going on here, right? And if you remember from our earlier discussions, it's industrial revolution happening, where we're starting to see the cumulative effects of all the fossil fuel burning, greenhouse gas emissions, that sort of thing. Now, we look at our knowledge in terms of global warming and climate change. So we know based off of data, we just showed it, right? The Earth's average temperature has been increasing since the 1980s. Initially scientists were looking at it, it's like, okay, we need to determine if this is, just natural climate change that's happening due to natural causes, or if it's based off of human activity. And what we see is that there's evidence of past climate change going back, almost 200,000 years ago, and it's showing a really close correlation between the concentration of greenhouse gases in the atmosphere versus global temperatures. And so what we have then are computer models and also other evidence that shows that relates to us what are some of the cause and effects that we're seeing with climate change. So for example, we have records of the amount of carbon dioxide in the atmosphere that show that we have a steady increase in that amount of carbon dioxide. And scientists can look at this by looking at gas bubbles that are trapped in glaciers. And so they can take those ice cores, they can look at those bubbles and analyze the gases that are in those bubbles to get an idea of the greenhouse gas concentration at that time. And so they can actually look at what the atmosphere was like, say, before the Industrial Revolution, and before the development of machinery. And that development began in the mid 1700s. And so, clarify, I believe I stated that this was the industrial, right? Brain fart, and I'm sorry. And so what I meant to say is not that this is, let me erase, not that this is the Industrial Revolution, but that we're really starting to see effects, right, from the Industrial Revolution leading into kind of our temperature change here, right? So it's late for me now, brain fart, sorry about that. So Industrial Revolution, mid 1700s, but we're seeing kind of what's happening with that accumulation of greenhouse gases from the time in which we started burning those fossil fuels. Satellite photos are also used as evidence for climate change, because we can look at the changes in the snow and the ice conditions. We can actually look at how snow levels have changed, say, over the last 50 years or so, or how glaciers are retreating over the last couple decades. We can also look at migration behaviors of organisms, and we can show how their migration routes are changing due to specific changes in climate. We can look at carbon dioxide content in the ocean because that carbon dioxide will dissolve into the ocean, and then it gets converted into carbonic acid, which is one of the big reasons why you have chloral bleaching, because of that ocean acidification process. And so we can measure all of these things. We can also look at changes in growing seasons of plants. We can physically measure how glaciers retreat or the thickness of ice sheets. We can look at increased carbon dioxide effects on photosynthesis. We can look at changes in wind patterns, ocean currents, measurements of sea level. We can look at the frequency and strength of tropical storms, and we're seeing an increased frequency, and we're seeing a larger percentage in those stronger tropical storms compared to what we saw, say, 20, 30 years ago. And so we can take all of this data and look at, or use that to really tell us what's going on with our climate, and use that to inform our understanding of climate change. And so it's not just models. We don't just take past climate data, put it into a model and say, okay, what will the future look like based off of these specific greenhouse gas scenarios? There's a lot of other physical data, experimental data that's showing, and even observational data that's showing, what effects our planet is going through that are suggesting effects of climate change. And we can directly measure changes of these greenhouse gases in the atmosphere. So if we look from 1960, where the concentration of carbon dioxide was 320 parts per million, it's now over 400 parts per million. And so that amount of greenhouse gas for carbon dioxide has increased really steadily. And this is a fairly high amount of carbon dioxide in the atmosphere. Methane gas is another greenhouse gas that we'll talk about here in a second. And, it's steadily increasing, right? So you see that slope there. And so, it's getting higher and higher as well, to where it's going to have an effect on climate and the changes that are going to happen over the next several decades. And so if we look at some of the principal greenhouse gases and what the sources are and what the impacts they have are, what we come up with is, these primary greenhouse gases. So carbon dioxide, methane, CFCs, and nitrous oxide. If we look at these in order, starting with carbon dioxide, this one is the most abundant greenhouse gas. And this one is responsible for 65% of the warming changes that we are experiencing around the globe. It occurs naturally. So carbon dioxide comes from organisms as they respire and from the fermentation process. But we put much more quantities of carbon dioxide as a function of, or as a product of, energy production, so the waste that comes from burning those fossil fuels. Another factor that leads to increased carbon dioxide in the atmosphere is deforestation. Okay, so when you cut down trees, you don't allow for those trees to take up carbon anymore. And if they're not fixing and putting carbon into their tissues, then that carbon is going to be in the atmosphere. And then if you cut down a forest and you burn that forest, not only are you removing a sink of carbon, but you are also emitting and releasing all of the carbon that was locked up in that biomass back into the atmosphere, or back into the soil, depending on how it breaks down from burning. When we look at the measurement from the observatory in Hawaii, so that figure we just looked at, We're, like we said, we went from about 317 parts per million to about 404. So that's 27% in what, 56 years. So that's a pretty big increase. Generally, the amount of carbon dioxide in the atmosphere prior to the Industrial Revolution was about 280 parts per million. So we've almost doubled that. So it's an increase of 45% compared to pre-industrial concentrations. So that's a big increase. Next, looking at methane. This is the second most abundant greenhouse gas. So we're attributing approximately 17% of global warming effects from methane. And this comes from biological sources and also waste products from fossil fuel use. There are microorganisms that release methane into the atmosphere. There is natural gas, so like methane, oil, and coal. That, I don't know why I say methane provides methane, but natural gas. Oh, I just can't read. Natural gas is primarily methane. There we go. And then oil and coal contain methane as well. And so when you burn those off, methane is released as a product of that conversion. Methane in the atmosphere currently is about 1850, so 1850 parts per billion. So look at the scale of this. So we said carbon dioxide was parts per million. So for every million molecules, you have that many carbon. And so this is for every billion, you have this many methane. And pre-industrial revolution, it was about 700 parts per billion. So that's more than double the concentration there. For nitrous oxides, so things like N2O, this is a small component of the greenhouse gas picture, and this enters mainly through fertilizers and fossil fuels. Certain soil bacteria can convert compounds into nitrous oxide, so things like fertilizers, they'll convert into nitrous oxide, and then that releases into the atmosphere. Next, we have the CFCs. So these are, again, a minor component, and these are synthetic compounds. These are not naturally made. So there are no natural sources for CFCs. They're pretty much used or were used as refrigerant gases. So like for refrigerators, air conditioners, we use them in cleaning solutions, aerosol containers. And even though they were present in small quantities, they are super efficient. They're about 15,000 times more efficient than carbon dioxide. And it was the major cause, like we talked about in the last chapter, for the ozone destruction. And the ozone, or I should say the CFCs, was scheduled to be eliminated by 2020, so last year. I should actually look up and see if they have been completely eliminated from products that they were in. So currently, looking at what we know about climate change, the IPCC was established in '88. And the IPCC is the Intergovernmental Panel on Climate Change. And this panel was put together to study climate change and to make recommendations on how we can reduce our effect on climate change and try to get it back to as natural of a process as we can. And so the IPCC provides assessments of our current knowledge on climate change, and they do so at regular intervals. So they have meetings every couple years, and they'll post a report, and you can look at that IPCC report publicly. So you could go to the IPCC website and you can download their most recent assessment report. The IPCC is actually broken up into several working groups. You have working group 1, 2, and 3. Working group 1 looks at physical science. Working group 2 deals with impacts of climate change, and working group 3 looks at how to mitigate the effects of climate change. And so you kind of have groups working on different aspects of the climate change problem, and trying to help find the solution to those issues. 2013, Working Group 1 published the 5th assessment report, and basically it was a culmination of 259 scientists from many places around the world, and over 600 people actually contributed material for the report. So it's really a collaborative effort where there are a lot of people kind of working together to look at this issue. And what their report basically stated is several important conclusions that were, basically stated in previous reports. So they reiterated those and said, okay, we're still seeing these, and these conclusions still, excuse me, these conclusions still need to be brought up. And then they also added several new observations. The first is that human activity is clearly influencing climate. Now notice we're not saying human activity is solely responsible for climate change. We're saying that we're clearly influencing how the climate is changing. Second is that there are increased concentrations of greenhouse gases, so carbon dioxide, and we know when you increase carbon dioxide, it leads to an increase in temperature. And so if there's a vast increase in carbon dioxide, and if that carbon dioxide is a product of human activity, then human activity is leading to an increase in temperature, right? This makes sense. And then the evidence of increased temperature is what they say clear, and we'll kind of look at this here. So the evidence that they have is that the Earth's average temperature has increased around 1 degree Celsius since 1880. The amount of spring snow and ice have decreased in the northern hemisphere, and the snow is melting earlier and earlier every year, meaning that it is warming faster in the spring. The number of cold days has decreased over a year, and the number of warm days has increased. And in the Arctic region, the polar region is actually warming more than the rest of the world. What the warming of the Arctic region does is it allows this permafrost to actually melt. And so permafrost is a permanently frozen soil. And the permafrost temperatures have increased 2 to 3 degrees Celsius, which is, upwards to 5 degrees in Fahrenheit. So that's significant. And the thickness of the permafrost layer has decreased. Now, there has been a reduction of area covered by Arctic sea ice at the end of the summer season, so in September. So that area is getting smaller and smaller. So habitats for that rely on that Arctic sea ice, or organisms that rely on that Arctic sea ice, their habitats are getting smaller. Ice sheets are losing mass. Glaciers are melting. And then spring is arriving earlier in many regions around the world. What they also found is increased carbon dioxide in atmospheres, and the temperature increase is affecting the oceans. 28% of the carbon dioxide emissions end up in the ocean. And if you remember, I said that carbon dioxide gets turned into an acid. So that increase in carbon dioxide dissolved in the water changes to an acid, and it causes that pH to decrease. So it becomes lower. So it becomes more acidic. And even though it's only a zero point 0.1 pH unit that it changed, that's a 26% increase in hydrogen ions, and that amount can really affect the organisms, and it has. We've seen a lot of coral bleaching, a lot of organisms not being able to build their calcium shells because that acid prevents them from doing so. About 90% of the additional energy added to the Earth has been stored in the oceans. So that's resulting in an increase of temperature change. Um, and so this temperature change is the upper 75 meters. The ocean has risen about 7.5 inches in the last 100 years. And the rate of sea level rise is increasing and is about 1/10 of an inch per year within the last almost 20 years. Okay, and so what this means is that coastlines are going to drastically change as sea level rises. And so National Geographic has a really good article on this, and they have these really good interactive maps that show the maximum kind of impact of maximum sea level rise. So if the sea level rises based off of the maximum prediction, so like worst case scenario, they have a map of the world where it shows coastal regions to be lost. And in that map, the Central Valley is an inland ocean or an inland sea. So it's very interesting. You get a lot of coastline loss. Florida is pretty much underwater. And in fact, my hometown is about an hour and 15 minutes from the beach. And my area would be underwater if that maximum sea level rise happened within the next 100 years. I think is what it is. That may be off on that, but I think it's 100 years or so in which those predictions are out there. And again, I think that's maximum sea level rise. And so we may not see that amount. It may be lower, or it could be higher, but yeah, so just take a look at that. And so it's really interesting. So if you're interested in it, just take a look. You just Google National Geographic sea level change, and that article should come up with the interactive map. And so the consequences of climate change. So if you look at the overall climate change, you get an increase in the average temperature of the Earth. And you may say, okay, we're talking about 0.8 degrees Fahrenheit here. Where were we at? 2 to 3 degrees Celsius there, so 5 degrees Fahrenheit. That's really not a bit, that's not a lot. It's not like an extreme warming event. But it only takes a little bit of change to push an ecosystem over the brink. I mean, some of these ecosystems are really fragile, and you can imagine them like sitting on top of a pyramid and being balanced on top of that pyramid. And if you just put a little bit of weight on one side, it slides off the top of that pyramid and basically falls over. So a lot of these ecosystems are very, very fragile, and these small changes could set in motion changes that would significantly alter big regions around the world. So for example, we're saying that the Greenland ice sheet is melting and it's going to lead, let's say 3 feet in sea level rise, right? And you're like, oh, I lose 3 feet of the coastline around the world. No, like, we'll figure it out. We'll, figure out how to cope. But that amount of water, of fresh water, cold water that enters the Atlantic Ocean could change the flow of the Gulf Stream. And if the Gulf Stream changes, all of a sudden you have a change in a warm current that is allowing Europe to be at a warmer climate than what it would be based off of its latitude if it didn't have the Gulf current going by it. And so Europe could go into a freeze. And that could also change climates in other places. And so even though it would just be a small temperature change and say, a small change in sea level rise, it could really throw out the ocean currents, and we could see a drastic change in climate. And so if you want to see an extreme kind of version of that, that is what The Day After Tomorrow, the movie, basically discusses, is if something really extreme like that were to happen. I don't think all of that is based off of actual science. I'm not 100% sure. I think some of it is fictionalized, but the capabilities of that Gulf Stream changing is there, and you could see really big impacts. So that much is based off of science. And if you're interested, you can kind of look up that one too. But it is kind of a neat thing to look at, and interesting to think about. And so with these consequences, we have various computer models that say that raising temperature will lead to changes in the hydrologic cycle, sea level, like we talked about, survival and the distribution of organisms. And a lot of my research for my PhD looked at this factor, the distribution of organisms. And based off of just me looking at mammals in North America, you're going to see some big changes in the mammalian community by the year 2100, heck, even by the year 2050, based off of even the moderate expectations, not even the extreme changes that we could predict, but just moderate if we did curb our carbon emissions. And a lot of the species that I looked at just aren't capable of keeping up with those climate changes, and we could see several extinctions happen if those species aren't able to adapt and cope with that. And so, this is going to be a big thing moving into the future as well. And also, like we mentioned, with sea level rise, human settlements aren't going to be able to get out of the way of that rising sea. I mean, they're going to have to leave homes, move inland, and not be able to deal with that. But some will. Some will be able to adapt and change. But there are going to be some that's really going to be hit hard because of that. And a lot of the places that are going to be kind of on that brunt are the poorer nations, because they're more vulnerable to those effects of climate change. They're more dependent typically on economic activity that is climate sensitive. So remember, we talked about those poorer nations being really dependent on their local natural resources, subsistence agriculture. And if those resources change because of global warming, so let's say there's a species that they harvest, from meat or bush meat, and that species goes extinct, or it migrates out of their region because of climate change. Now all of a sudden they don't have access to that resource. There are people that live on the coast so that they can fish. With sea level rise, their villages are going to be basically underwater. They're going to have to migrate. They're going to have to move, start over. They hopefully can adapt, but it's going to be overall a big, difficult change for them to deal with. The IPCC has actually identified Africa as the continent most vulnerable to the impacts of climate change because of its widespread poverty limits adaptation capabilities. So if you don't have the money, if you don't have the economic flow, that financial flow to help you adapt to these changing issues, then you're just not going to be able to do it. And so looking at how the hydrologic cycle could be changed, remember when we talked about the water cycle, we talked about evaporation, precipitation, infiltration into the groundwater, runoff, so water flow. All of that is technically driven by energy, right? And so that primary source of energy is the temperature, right? So evaporation, water evaporates because of temperature. It condensates and precipitates when it cools down. And so that's really driving that cycle. And so if you change the temperature and you change the amount of heat that's trapped and solar radiation that's trapped um, in the atmosphere because of increased greenhouse gases, then you're going to have a temperature change that is going to affect that hydrologic cycle. So we're going to affect weather and climate. And so just if you don't know, to define these, weather are the day-to-day changes in the temperature, precipitation, wind, snow, and so that is kind of what you get every day in terms of a climate aspect. Um, Climate itself is the long-term average of weather patterns. And so basically the saying is, weather is what you get, climate is what you expect. And climate is typically determined based off of a 30-year average, right? So over the past 30 years, we would look at climate data and you would get an average. So the average temperature for the last 30 years has been 70 degrees, right? So that doesn't mean that every day is going to be 70 degrees. Every day you'll have different weather patterns. But over the long time frame, if you averaged out your temperature, you would get 70 degrees for that location, right? And so climate is, or weather is what you get, climate is what you expect. And so those higher temperatures are going to increase evaporation. That's going to cause areas to become drier. And then the increased moisture in the atmosphere will have greater rainfall in other areas. You'll have snow patterns to change. Other areas, some areas are going to get less snow, some areas are going to get more snow. Because that evaporating water, it does have to go somewhere. And so just because one place gets drier and it's going to get warmer doesn't mean that everywhere is going to get drier and warmer. Those atmospheric patterns just may change because of climate change. And so other things we expect to see based off of data and research is that you're going to get spring snow decrease, so the amount. It's going to melt earlier in the year. Tropical storms, hurricanes are expected to be stronger. There are going to be more hot days, fewer cold days, and then you'll get spring arriving earlier, causing issues with species migration patterns, with when flowers bloom, etc. That's just going to change a lot of behaviors in organisms. Now, the other issue from climate change that we mentioned is a rising sea level. So with a warmer Earth, you get sea levels to rise for two reasons. Water increases in temperature, so it takes up more space. When it gets warmer, basically expands. Whenever you have higher temperatures, you also get melting of glaciers, melting of ice sheets. When those things melt, that fresh water goes directly into the ocean. And that is enough water going into the ocean to lead to sea level rising. Rising sea level will erode beaches. It will inundate. So basically what that means is that area will now be underwater, so low-lying areas. And then it increases the vulnerability of coastal areas to flooding whenever you get big storms and lots of rainfall. So by 2100, sea level rise is expected to range anywhere from 10 to 39 inches. The scenario that I was mentioning, I believe, is around this higher mark. So this is 3 feet. This is a substantial increase in sea level rise, a little over 3 feet actually. If we get a 50 centimeter, a 20-inch rise in sea level, you'll get a substantial loss of coastal land in North America, especially along the Gulf Coast, along the Atlantic. And some of these cities are going to be inundated, or they're going to have significant flooding and saltwater intrusion into their cities. Worldwide, we have about 600 million people living in low-lying coastal areas. So that means 600 million people are going to be displaced because of sea level rise if that happens. So if we get that amount. The land area in some island nations could dramatically change as flooding happens. And so let's just take a look at a barrier island. So this is like a barrier island, a barrier spit. This is in 2014, right? You can see kind of this house in the picture and this dock in the picture, right? So we had Hurricane Matthew come through on the East Coast, and it completely changed the dynamics of this barrier spit. It rerouted the sediment. It created this flow, right? Basically this inlet. So now you have water coming in and out, completely removes vegetation. It now blocks, sediment blocking this area. And so that's going to change the sediment flow pattern. And so now a sediment was flowing down the shoreline like this. Now you'll get a different sediment flow. So it's not going to go like this anymore. Depending on how the currents are, you may continually get a buildup here. You may get a buildup here. And so it's going to change the current patterns here on the beach. And these houses are directly going to be affected because of that. And you can already see, it looks like the boardwalk here. Let me erase these lines. Looks like that boardwalk that was here is completely gone. And so these houses are already directly affected. So big change in that area. And that's just from a storm surge, from a powerful hurricane, right? Imagine what permanent long-term sea level rise would look like. In terms of health effects, the most direct effect of climate change is the hot temperatures, so leading to, say, heat exhaustion, heat stroke. If you have already present health conditions, you're going to be heavily affected by the increase in heat and the more hotter days that we're going to get. In 2010, there was a record-breaking heat wave in Russia. 62 consecutive days of above normal temperatures. There were about 11,000 deaths attributed to heat-related, or they were heat-related. In 2013, you have the U.S. Southwest, several record temperatures, several deaths, and as we now know, 2013 to like 2017 or 2016, I think it was 2017 that was our wet year in California, was an unprecedented drought. And so even though, temperatures in the U.S. were higher than in Russia, the number of U.S. deaths were lower because we were equipped to already deal with that. The Southwest is already a hot place, so we have air conditioners. We're ready for those type of conditions, more ready than what the Russian population was. A lot of their buildings don't have air conditioners because they don't really need them on a regular basis. But as temperature increases, they'll start to need those air conditioners maybe a little more. Heat also affects pollution. Air pollution becomes worse because as temperature increases, you get more ozone at ground level. So that leads to health issues. And the children and the elderly are more vulnerable to these. And so they're really going to suffer disproportionately because of warmer temperatures that lead to poorer air quality in our areas. what rising temperatures also contribute to is the prevalence of diseases, and those will increase. And so particular diseases will depend on local climate. And so, for example, some diseases really only appear in warm areas because those vectors, so like mosquitoes are a vector, they thrive in warm, moist areas. So as Earth becomes warmer, some of these tropical diseases may spread to other parts, because right now, right, say we have the Earth, very bad Earth, say we have the tropic, right, and this is where your warm area is, but as the Earth warms, so this is where your diseases may be constrained to, so this area. But as the Earth warms, this average temperature may now occur up here, right? And then this average temperature may now occur down here because of the average warming. So now the diseases are found here. And then as it warms again, they will expand and move poleward. And so they'll occur in places that they wouldn't naturally occur. And so again, those vectors are things like mosquitoes that are bringing diseases like malaria, dengue fever, encephalitis, yellow fever. And with warming, you could also get more algal blooms. That's going to occur more and more often. And remember, we talked about eutrophication. We talked about dead zones. We mentioned algal blooms could be toxic to certain organisms. And so really big effects from that rising temperature. And so when you have increasing temperature, like I mentioned, you're going to have changes to ecosystems. And some ecosystems will maybe be more resilient, some won't. And so we'll have changing ecosystems in terms of species distributions changing. So species will go into ecosystems, species will leave ecosystems. You'll get sea level rise to change those low-lying areas and shorelines, ocean acidification changing coral reefs and other habitats in the ocean. And so we expect to see lots and lots of changes to ecosystems as climate change happens in the near future. Climate's also going to affect the agricultural and food supply industries. Yields will go down because you'll have more heat stress, you'll have drought in other areas. Regions that receive increased rainfall and warming, yields will increase. So the areas that are the primary agricultural areas now may not be so in the future because climate may change, and then other areas may have to start farming in those areas, whereas other areas may have to move away from ag because climate is just not conducive to that activity anymore. More severe weather can cause more crop damage. Warmer climates will reduce the flexibility in crop distributions and irrigation demands. And so like we mentioned, we're going to have to potentially move areas of ag, and that means that the areas that already have infrastructure for irrigation, that infrastructure is just going to be there and not be needed. And then other areas that are getting ag now will have to have new infrastructure put in, and so there's going to be some issues there. And then again, geographic ranges change, so you'll get pests to move around, and then you'll also get changes in how we use pesticides and the resilience of pests to those pesticides. And so looking at how we can address climate change, basically we want to improve energy efficiency, because not only does that reduce the amount of greenhouse gases that are being released, but it also conserves what resources we have left. And so it makes sense to increase energy efficiency, even if climate change wasn't a concern, because by increasing our energy efficiency, we're saving our resources, right? We're conserving our resources, and we're making our resources last longer. So even if climate change wasn't an issue, we should still be looking to conserve our resources and to be energy efficient. So one way to kind of move towards greater efficiency would be potentially to place a tax on the carbon individuals, or I should say the not carbon individuals, the amount of carbon that individuals and corporations release. So if they release more, they get taxed more. If they release less, they get taxed less. This would increase the cost of fuels. It would stimulate a more demand on efficient fuel products because that cost would rise. It would also stimulate the development of alternative fuels because, again, fuels will increase and become more costly, especially those that are lower on carbon content because they would avoid that tax, right? And so you're looking now at alternative fuels and alternative technologies. We also reduce the greenhouse gas emissions. That's going to have important benefits that could offset costs. So greater energy efficiency really leads to lower air pollution. So you have lower healthcare costs because you don't have as many respiratory issues because the air you breathe is not as polluted. And so in China, there was a study that suggested that 1.6 million premature deaths occurred in 2015 due to air pollution, which is a lot. That is a lot of deaths because of air pollution. Again, that could be fixed. Green sources of energy that we could use are things like wind power, solar power, hydroelectric power, as well as nuclear power. You know, we have to be mindful about how we do build and utilize the infrastructure for these. But these are good because they don't release carbon dioxide, and some of these are renewable. And so switching to those green sources is really the most effective way to reduce our carbon emissions. And then we also need to think about how we're affecting ecosystems that have a role in storing that carbon. So for example, we mentioned that forests store carbon. So there's a lot of carbon in the biomass of these trees. And when you cut those trees down, they're not taking in carbon anymore. And if you burn them, you're releasing the carbon that was stored. So again, you're taking away a sink and you're adding to the amount of carbon in the atmosphere. And so since carbon is important for living things, what happens to the biomass really affects that carbon cycle. And so forests, as we know, contain tree species that can live for hundreds of years, and so they effectively remove that carbon from the atmosphere for centuries, depending on the age of the tree. And so preserving forests slows the rate of the increase of atmospheric carbon dioxide, especially when those tropical forests, because they can remain unmodified for a long period of time. But again, when you burn those tropical rainforests for farming and grazeland, you're adding it to the atmosphere and you're removing that as a source, as a sink for carbon dioxide. There's an estimate that was published that said that 20% of the additional carbon dioxide entering the atmosphere comes from deforestation. So a fifth of the carbon dioxide we have in the atmosphere as a result of removing trees. Planting trees, making new forests, it has been suggested as a way to potentially reduce carbon dioxide because you're making a sink for that carbon. Although some argue that this is only a short-term benefit because those trees will mature and die. Their decay will release carbon dioxide at some point later in time, but at least it kind of gives us a buffer to develop new technology. So, you know, you put a lot of forests out there, those forests will last for say 100 years. So we've got a little bit of time for a buffer, but again, forests aren't taking up all of the carbon, right? So we said that 20% has been cited as being released due to deforestation. So if we did take 20% in, we still have 80% to deal with. So it's not a solution, but it can help in terms of the greenhouse gas emissions problem. And so now looking at kind of technological approaches. So the Department of Energy says that relying on already proven technology could reduce carbon emissions by almost 400 million metric tons. This is enough to bring emissions down to levels that were at 1990 comparison. And so let's just kind of look at that. I know we're going back here, but let's just bring this figure up. See what 1990 looks like. 1990, right in here. All right, so we're looking at about 350. That's a pretty big drop. And that's a big drop. If we can get those emissions back down to that, just by using technology that we already have. So we don't have to develop any more technology. All we need to do is implement what we already have and make efficient use of the technology that we already have. And that can lower our emissions substantially, right? And so it's something we kind of need to look at and dig into more. There are a lot of technological approaches that have been suggested to limit carbon emissions, carbon dioxide emissions. Again, those renewable resources that we looked at. But because fossil fuels currently provide 90% of the world's energy, converting to a greater kind of reliance on non-fossil fuel green energy, you're going to have to construct new infrastructure to make that happen. The technology's there, like we said, to get it down, but to get it down even farther, we need new technology. But again, just to get it down and utilize that technology and put that in place, you're going to have to do some construction to get that infrastructure in place. Another approach to the carbon problem is just to prevent it from being released into the atmosphere. Carbon dioxide can be reacted with other compounds to produce solid minerals, carbonate minerals. So like limestone, which is calcium carbonate, that you then can store in landfills and basically serve as a sink that prevents that carbon dioxide gas to be released. You can also capture and store the carbon dioxide and prevent it from being released into the atmosphere. But again, all of these, while they could help, and they will help if we use them, they come with a cost that is going to be put on the consumer of the energy. And so as long as fossil fuels are less expensive, then it's going to be difficult to get people to want to convert over to those green energy sources. Again, because we only have so much in terms of finances in order to take care of our families, and we don't want to be putting most of our salaries into energy that we use. And so not only do we need to look at reducing the amount of energy, but we need to reducing the amount of energy used, but we need to look at how we can kind of convert into green energy while keeping it cheap. And so we've got to kind of figure out technology to help us do that. And so just finishing up with international agreements. So we've talked about one where we phased out the CFCs that help with the climate, the issue of climate with the ozone layer. And, that was the Kyoto Protocol, where we decided to reduce the CFC issue. And the United States actually didn't officially ratify the treaty, but we did participate in climate change conferences later on. And so under that Kyoto Protocol, the economically developed countries were required to limit the greenhouse gas emissions below 1990 levels. They had to meet their targets by 2012, and the developing countries including Latin America, Africa, Asia, did not have binding targets, but they still could focus on meeting targets. Um, 2006, China became the world largest emitter of carbon dioxide. United States, we're in second. And Americans, however, still cause more pollution per person, so per capita, than any nation. It's a big deal. European countries have been most successful in reducing greenhouse gas emissions. They're really kind of pushing towards these green energy use. Industrialized countries are promoting change to reduce greenhouse gas emissions. But in 2017, we kind of withdrew, the United States withdrew from the Paris Agreement. And there's only 3 countries that really remain in that agreement. And I should look and see if that's the current one to date. But at the time, which was, I believe, 2020, it was 3. Other heavily industrialized countries are meeting goals because of the economic downturn. So, for example, European countries, when the economy's bad, energy use declines, can't really afford to do things, can't use as much energy, so carbon dioxide emissions fall. If you notice with the pandemic, when we stopped using cars, places, atmospheres, big cities' atmospheres cleaned dramatically. There were some cities that were posting pictures of mountains that they really weren't able to see, in the last several decades, which is amazing to think, right? Just because we had closed down these cities for a couple of months to a year, and I should actually say a couple of months, because these pictures were being posted like a few weeks, a month or so after, lockdown was initiated, and climates were changing quickly because of that. It's just mind-boggling to see those effects, and we just really don't pay attention to that on a daily basis. And so the Kyoto Protocol expired in 2012. There was a meeting in Qatar in 2020, and an agreement was reached to extend the protocol through last year. And so Europe in general met its goal for greenhouse gas emissions. Most developing countries did not have goals to meet. So greenhouse gas emissions have continued to increase. And so, yeah, so that's it for chapter 17. We've got 2 more chapters to go. So almost there, so 19 and 20. These are the summary slides for chapter 17. As always, make sure you look at those, you go over those, you use them as a study guide. Again, this is not all the material you need to study for this chapter, it's just a good starting point. And let me know if you have any questions, if you have any concerns. Feel free to email me, contact me through the discussion board. And as always, I hope you have a great, safe day, and we will see you in the next chapter.